We have seen that chemical reactions are driven by differences in chemical potential energy, and that most of the time this energy difference is released as heat. But how fast do reactions happen? How can we understand the effects of reactant concentration and temperature on the rates of chemical reactions? And how can we change those conditions to take better control of reactions to better serve our needs? All reaction rates are measured as a change in concentration per unit time. The standard units for reaction rate are moles per liter per second, although sometimes you might see rates quoted in molecules per cubic centimeter per second. Looking at this balanced reaction for the decomposition of hydrogen peroxide, we see that 2 moles of H2O2 are destroyed for each mole of O2 produced. Therefore, we must divide the measured rates by the respective stoichiometric coefficients to get a consistent definition of the reaction rate. Note that when we measure the disappearance of reactants, we include a negative sign to ensure that all reaction rates are positive numbers. The initial rate is measured at or near the start of a reaction when the concentrations are known, and the instantaneous rate is measured by using extremely small time increments, although this can introduce large uncertainties in the measurements. Normally, only a small fraction of hydrogen peroxide decomposes over the course of a year at room temperature. The opaque plastic bottle keeps out room light, which can cause photodecomposition. But by adding a catalyst, like potassium iodide, the decomposition reaction can be greatly accelerated, as shown here by Science Bob Pflugfelter on Jimmy Kimmel Live. This popular demonstration is called elephant's toothpaste and is conducted with added detergent and dyes to dramatize the rapid release of oxygen in the reaction. Elementary reactions are changes in chemical bonding that take place in a single step. In the gas phase, they take place during a single collision. In solution, collisions are not well defined, so we say that the reaction takes place in a single encounter of reactants. Collisions or encounters are proportional to the concentrations or partial pressures of reactants. So for unimolecular reactions like the decomposition of N2O4, the reaction rate is simply proportional to the N2O4 concentration, and we call this a first-order reaction. The constant of proportionality is called the rate constant, K, and for all first-order reactions, the units of K must be inverse seconds for the rate to have units of moles per liter per second. For bimolecular reactions, there are 2 cases. The first involves collisions of 2 molecules of the same type. The reaction rate is proportional to the square of the NOCl concentration in this example, so we say that this is a second-order reaction. Notice that the rate constant must have units of inverse moles per liter, inverse seconds, for the reaction rate to have the proper units. The second case involves collisions of different types of molecules, so we say that this reaction is first order with respect to methyl bromide, first order with respect to hydroxide, and second order overall. We see that for either case, the experimentally measured rate constant for any second-order reaction must have units of inverse concentration, inverse seconds. For elementary reactions, the molecularity determines the order of reaction, because the overall rate is proportional to the collision rate. However, the converse is not true. The reaction order does not necessarily determine the molecularity of a reaction, because often a reaction will take place by means of a multi-step reaction mechanism. Based only on the balanced reaction, we might guess that the decomposition of dinitrogen pentoxide should be bimolecular, and therefore second order in N2O5 concentration. However, experiments show that the reaction exhibits first-order kinetics, and K has the required units of inverse seconds. We can rationalize why this is the case by postulating that the reaction occurs in 2 steps. The first step is slow compared with the second one, so the overall reaction rate is limited by this slow unimolecular breaking of one of the NO bonds to the central O atom in N2O5. But even though the overall kinetics are first order, the reaction is not unimolecular because more than one reaction step is required. We will consider other more complicated types of reaction mechanisms in a companion video. There are two general approaches to determining the rate law for a reaction, which is shown in the box for a hypothetical reaction of molecules A and B. The first approach is called the method of initial rates. In this method, the reactants are quickly mixed at a known initial concentration, and a small change in concentration is measured after a short time interval, delta T. The small delta T ensures that the extent of reaction is small. The reaction order N, with respect to A, is determined by a series of experiments varying the initial concentration of A while holding B constant. A plot of the logarithm of the measured rate versus the log of initial concentration A will have a slope equal to N. A similar series of experiments varying the initial concentration of B while holding A constant can be used to determine the reaction order M with respect to B. With both N and M in hand, we can use any of the experiments to determine the value of K and assign it the proper units to complete the determination of the rate law for the reaction. A second method of determining the rate law for a reaction uses integrated rate expressions. Using the tools of calculus, we can integrate the rate law for a first-order reaction to predict that the concentration of reactants will decrease exponentially with time. A strong advantage of this method is that we can allow the concentrations of reactants to decrease almost to zero, so this method is useful for fast reactions. The predicted half-life for any first-order reaction is log 2 divided by the rate constant. Notice that the half-life is not dependent on concentration, so measurements of subsequent half-lives should all give the same value. This is a unique aspect of first-order kinetics. For reactions that are second-order in a single species, we can similarly integrate the rate law to predict the concentration of reactants as a function of time. The initial rate is fast, but then the reaction slows considerably. The half-life for this type of reaction is inversely proportional to the initial concentration, so the half-life gets longer and longer as the reaction proceeds. The integrated rate laws for first-order and second-order reactions have distinctly different shapes, so we can use nonlinear curve-fitting techniques to determine which model is a better fit to our experimental data. However, it's easier and more common to make two different types of graphs for this purpose. The first graph is a plot of the logarithm of concentration as a function of time. If the reaction exhibits first-order kinetics, this plot will be linear, as shown here in blue, and the slope of the best fit line to the data will be equal to minus k. However, if the kinetics are not first-order, the plot will be nonlinear, and a first-order model can be discarded from consideration. The second type of graph is a plot of reciprocal concentration versus time. Here, a reaction exhibiting first-order kinetics will be highly nonlinear, but second-order kinetics will give a straight line where the slope is equal to the rate constant k. The vertical axis values have units of reciprocal concentration, so if the time is plotted in seconds, the slope gives the proper units of inverse moles per liter inverse seconds for the rate constant k. So far, we have only discussed the effects of concentration on reaction rates, but it turns out that temperature has a very large influence as well. There are two reasons for this. First, the collision rate depends on molecular speeds, so a higher temperature means a faster collision rate. But more importantly, most reactions exhibit an activation energy threshold that represents an amount of energy required to partially or sometimes completely break chemical bonds before energy can be recovered in the formation of new and stronger bonds. The Boltzmann distribution of collision energies usually ensures that only a tiny fraction of collisions have a sufficient energy for reaction, but this fraction is extremely sensitive to changes in temperature. In 1889, a Swedish scientist, Svante Arrhenius, proposed that all reactions follow a simple temperature dependence as shown here. We now know that the detailed temperature dependence for most reactions is more complicated, but over a sufficiently small range of temperatures, this equation is usually sufficient. It is simple enough to conduct a few experiments at different temperatures and then plot the log of K versus reciprocal absolute temperature, in kelvins, to determine the activation energy, E sub A, from the slope of the line. We can also determine the Arrhenius pre-exponential factor, A, from the y-intercept of the linear fit to the experimental data. We saw earlier in this video that adding a catalyst to hydrogen peroxide can greatly accelerate its decomposition. Catalysts are widely used to speed up lots of different types of reactions. Many polymers and plastics contain living catalysts that cause small molecules to bind together as larger ones at moderate temperatures, where undesirable side reactions can be controlled. Your car has a catalytic converter for converting toxic gases present in engine exhaust into water, nitrogen, and carbon dioxide. And life itself would not be possible without enzymes, which are naturally occurring biological catalysts for converting food into nutrients and energy for life. One of the most important applications of kinetics is in atmospheric chemistry. For example, a detailed knowledge of kinetics allowed Mario Molino and F. Sherwood Rowland to discover how man-made chlorofluorocarbons, or CFCs, have destroyed part of the ozone layer in our atmosphere that normally protects us from harmful ultraviolet radiation. For this discovery, the two scientists shared in the 1995 Nobel Prize in Chemistry.